Okay, this is our new chapter. The time response, it is easy. It is not very difficult one. Time response. Some concepts we have to grow after studying this one. Poles, zeros, and system response. These are important concepts. Okay, see that definition here. The poles of a transfer function are the values of the Laplace transform variable s that cause the transfer function to become infinite, or any roots of the denominator of the transfer function that are common to roots of the numerator. The poles of a transfer function are the values of the Laplace transform variable s that cause the transfer function to be infinite. That means the values of the s for which the transfer function would become the infinity is known as the pole. Okay, that value of that s. Okay, this is the pole. Similarly, 0 means for the value of s for which the transfer function would be 0 is called the zeros. Okay, poles and zeros, two things. What is the pole and what is the zero? So what is the pole? For the value of pole is the value of s for which the transfer function would become infinite, and zeros are the values of s for which the transfer function would become 0. Okay, these are the two things you have to remember. So I am underlining here the poles of a transfer function are the values of the Laplace transform variable s that cause the transfer function to become infinite, and the zeros of the transfer function are the values of the Laplace transform variable s that cause the transfer function to become 0. Okay, this one and these two definition we have to understand. Poles and zeros of a transfer function. Okay, so let's take an example. See, it is a transfer function example. Cs is equal to s plus 2 divided by s into s plus 5. So if I break it, a by s plus b by s plus 5, or we can find this thing. Okay, so if I put the value s is equal to 0, if I put the value s is equal to 0 here, then I'll get the value of a, which is 2 by 5. Do you know how we have found this? Let me show you. S plus 2 is equal to a into s plus 5 plus b into s. Now if I put the s is equal to 0, is equal to 0, so 2 5a. So therefore a is equal to 2 by 5. Again s is equal to 5. If I put the s is equal to minus 5, so see here, so minus 5 plus 2 is equal to, this would be 0, minus 5b. Why minus 5? Because I want to make a 0. So it would be minus 3 is equal to minus 5b. Therefore, b is equal to 3 by 5. 3 by 5. Okay, so b is equal to 3 by 5. So here you have to do one thing, multiply the both end by s into s plus 5, then you will get this equation. From this equation you can find out the values of a and b. Okay, so this is the Laplace form in frequency domain. Now if I want to convert it to the time domain, though you have to make it the inverse Laplace transform, then you will get the 2 by 5. 1 by s means 1, and 1 by s plus 5 means e to the power minus 5t. Why minus 5? Because it is positive. Okay, so this is the poles in zero. It is example of CT. Now see this. Here Rs, that means the input is 1 by s, Cs is the output, this is the transfer function, s plus 2 divided by s plus 5. S plus 2 divided by s plus 5, this is the transfer function. Okay, so the values will be changed. The values will be changed, like s plus 2 by s plus 5. So if I put the value as the minus 2, if I put the minus 2 here, then see it would be 0. That means the full term will be 0 if I put the minus 2. If I put the minus 5, then it would be infinity. It would be infinity. That's why it would be poles. So zeros, let me clear to you. Okay. See this is a plane. This is called S plane. This plane is called the S plane. This is the S plane. This is the S plane. And this is the poles. This is poles. And this is zeros. This is poles, this is zeros. Okay. This is poles and this is zeros. Now put the values here. Say s plus 2 divided by s plus 5. Now if I put the value as s is equal to say minus 2, if I put the value s is equal to minus 2, then it would, what would happen? Then minus 2 plus 2 divided by minus 2 plus 5. So it would be 0 divided by 3. So which will become 0? So at the minus 2, the output would be 0. So what would happen if I put the value minus 5? Minus 5 plus 2 divided by minus 5 plus 5. That means minus 3 by 0. That means the infinity. Okay. So if I put the minus 5, then it would be the infinity. So that is the thing. For the value of s for which the transfer function would become the 0, would call the zeros. For the value at which the transfer function would become infinity is called the poles. Okay, so zeros and poles. This is the concept of poles and zeros. Okay, similarly they explain here. See this. Here, see the input pole. Here is the input pole. Okay. If I put the value s is equal to 0 here, okay, if I put the s is equal to 0 here, then it would be infinity. So at the center there is another pole. And some poles are there, like some zeros are there, like at these are the zeros values. Okay, these are the poles values. Here, this is called the forced response, and this is called the natural response. Okay, so these are poles and zeros concept of the poles and zeros. Okay. Now see, zero input pole. So input I am giving the step response, so I can change the s. That means if I put the s is equal to 0, then whole thing would be infinity. Here if I put the s is equal to -5, then the whole thing would be infinity. So -5 and 0, those are the pole, and the zeros 2 by 5 and 3 by 5, these values. Okay, now a pole of the input function generates the form of the forced response. That is, the pole at the origin generated a step function at the output. See, the pole at the origin generated a step function at the output. What is the step function? Do you remember? Step function is like that. This is the step function. This is the step function. This is a step function. The pole, see, the pole at the origin generated a step function at the output. So pole at the origin generated the step function at the output. Okay. Another thing, a pole of the transfer function generates the form of the natural response. A pole of the transfer function generates the form of the natural response. Okay. A pole of the input function generates the form of the force response. So remember this thing. Which are the force response? Which are the input response? So which are the natural response? Okay. And a pole on the real axis generates an exponential response. Another conclusion. The zeros and poles generate the amplitude for both the forced and the natural responses. Amplitude, that means 2 by 5, 3 by 5, those are the amplitudes. Okay. These are the conclusion they gather here. No, I would not see this. Now come to the point. That is the first order system. First order system. Here the input Rs, output is Cs. So Gs is equal to A by S plus A. That means this is the transfer function. Okay. First order system. We now discuss first order systems without zeros to define a performance specification for such a system. A first order system without zeros can be described by the transfer function as shown in the figure 4.4a. If the input is unit step, that means the Rs is equal to 1 by S. Say Rs is input is 1 by S. Input is 1 by S. The Laplace transform of the step response is C by S. Is Cs. Laplace transform of the step response is Cs. See, this is the step response. So Cs is equal to Rs into Gs, definitely. So Gs is into this one. Okay, now if I want to find it out, let me explain this thing. See, A by S into S plus A is equal to A by S plus B by S plus A. Now, if I multiply it by S into S plus A, then what would happen? A is equal to A into S plus A plus B into S. Okay, B into S. Now what would happen? Let's say now I put S is equal to 0. If I put S is equal to 0, then what would happen? When S is equal to 0, if I put S is equal to 0, A is equal to AA. So capital A is equal to 1. If I put S is equal to 0. So if I put S is equal to minus A, if I put S is equal to minus A, then what would happen? A is equal to minus BA. So is equal to minus 1. Okay. Okay. So B is equal to minus 1 and A is equal to 1. We have found this. So we can write what? We can write like this. CS is equal to 1 by S minus 1 by S plus A. So if we convert it to the time domain, so we'll get what? We'll get the 1 minus e to the power minus 80. E to the power minus. So this is the output. So here, this one, first one is the forced response, second one is the natural response. That's why it's called it CNT and CFT. So 1 minus e to the power minus 80. Okay. Now what would happen? See this. Now if you put the value of t as 1 by a, then it would become e to the power minus 1. In that case, this is the 0.37, the value of this e to the minus 1. So 1 minus 0.37, so that is the 0.63. Okay. So here the CT, that is the output response, is 0.63. This thing can be explained through the figure. That is called the first order system response. First order system response. This is a system response curve, this kind of curve. Here some values are there. So we have to know those values. We have to know those values. Like, see, this curve has some value like time constant. 1 by A. 1 by A is called the time constant. So it started from the 0, 1 by A, 2 by A, 3 by A, 4 by A, 5 by A, 5 by A, like this. It will increase. It started from the 0. Okay. So 0 to 4 by A is called the TS. TS means the settling time. TR 1.1 to 0.9 is called the response time. Sorry, rise time. 0.1 value is the 0.1 to the 0.9. 0.1 to 0.9 is called the rise time. And 1 by A is called the time constant. 1 by A is called the time constant. 1 by A is called the time constant. So this is the curve. This is called the response curve. And 63%, where is the 63% here? 63% of final value at t is equal to 1 time constant. This is the 63%. At 1 by a, we have found the 63%. Okay, these are the values. Okay, some equations are there like what is the time constant? Time constant is 1 by a. Okay, and rise time. Equation of rise time is 2.31 by a minus 0.11 by a. So this is the 2.2 by a. Okay, this is the rise time. And settling time 4 by a. Rise time, settling time. Okay, those are the values. Rise time 2.2 by a, settling time 4 by a.
Is that one, sir, a constant value?
Yeah, constant values. Just you, if you have the value of a, then you can easily find out. Okay, so the value of a will be given. Let's look at the example. See, this example, a system has a transfer function gs is equal to 50 by s plus 50. Find the time constant tc, settling time ts, and the rise time. So look at the values here. So we have the gs 50 by s plus 50. So here a is equal to 50. A is equal to 50. If a is equal to 50, then we can find the time constant, which is 1 by s. So which is 1 by a. That means 1 by 50. And we have the rise time. Value of rise time is 2.2 by a. That means 2.2 divided by a means 50. And settling time ts is equal to 4 by a. That means 4 by 50. So if you do calculation, then you will get the result. Those are the second, in unit would be second. Okay, so they said that. So time constant 0.02 second, t settling time 0.08 second, rise time 0.044 second. Okay, so easily you can find out. Now the second order system. See, second order system means the power of the S is 2. First order system, the power of the S is 1. Okay, like this. Okay. Here, now see this one. Okay, so this is a system. This is a general system. Now pole zero plot. Let us find out the pole and zero plot here for this system. Okay. So how to plot pole zero system for this plot? Okay. So first one, when see this kind of response, where the graph like this is called the overdamped. And where the graph like this, that is called the underdamped. And when the graph would be like this, then that is called the undamped. And the graph like this is called the critically damped. We'll understand how to write the graph. Okay, how to write the graph, draw the graph, we'll see. And there is a technique to find out this thing, how to draw the graph. There another plot thing. Okay, so here a thing, two thing would come. Natural frequency omega n. See, natural frequency. What is the natural frequency? The natural frequency of a second order system is the frequency of oscillation of the system without damping. Okay, that means without damping. That means continuously without any blockade. Okay, the natural frequency of a second order system is the frequency of oscillation of the system without damping. For example, the frequency of oscillation of a series RLC circuit with the resistance shorted would be the natural frequency. Okay, so natural frequency we consider it as omega n. Another one is this damping ratio. Damping ratio zeta is equal to exponential decay frequency divided by natural frequency. Exponential decay frequency divided by natural frequency radian per second, 1 by 2 pi natural period seconds divided by exponential time constant. Okay, there is a general equation like this. If you have this equation, it is a general equation like gs is equal to say b divided by s square plus as plus b. If we have this kind of equation, then we can write the omega n, that means the natural frequency square root of b, square root of b. Okay, omega n is the square root of b. So see this one. So b would be omega n square. So b would be omega n square and 2 zeta n. A is equal to A is equal to 2 zeta omega n. This is the value of A and B is the omega n square. So we have to remember this equation. From this equation, we will find the value of omega n as well as the value of zeta. Okay. Now look at the problem 4.3, example 4.3. A transfer function is given as this is the transfer function. So how to solve it? Let's see. That is what? Omega n square. Omega n square is equal to 36. So omega n would be square root of 36, or it is the 6. Okay, that is the omega n. Omega n. So 2 zeta omega n, again 2 zeta omega n is equal to 4.2. This one. So zeta is equal to 4.2 divided by 2 into omega n, that means the 6. 4.2 by, so if you put this value 4.2 divided by 2 by 6, so you will get the value which is a 0.35, which is a 0.35. So 2 zeta omega is equal to 4.2. This value is 0.35. Okay. Omega n square is the 36. Thus, you can find out the values of zeta. Now, another important thing will come around. Range of zeta. Okay, based on the values of zeta, you will find the response curve. What kind of output curve of the system? You will find this thing. Okay. So when the value of zeta would be 0, when the value of zeta would be 0, then the system response would be undamped. When the value of zeta would be 0, the step response would be undamped. Okay. Pole would be on the j omega axis. Pole would be on the j omega axis. And the zeta value range would be 0 to 1, and the pole would be on this region, and the system will be called the underdamped system. And the zeta value would be 1, then the pole will be like this, and this is called the critically damped. When the zeta value is greater than 1, then that would be called the overdamped. Okay, and the zeta would be here. Okay, so remember this thing, range, this chart. You have to understand this second order response as a function of damping ratio. Okay, so you have to understand this curve. Look at here. When the value of the zeta would be 0, the response would be underdamped. When the value of the zeta would be 0 to 1, then it will be underdamped. And when the zeta is equal to 1, it is critically damped. When the zeta is greater than 1, it is overdamped. Okay. Now see, important example, which is the example 4.4. Like previous example, you have to find out the value of omega n as well as the zeta. So when you find the zeta, then you will understand, then you can say the response. Okay, so I think let me show you one. First one, let's say this one. Okay, omega n square is equal to 12. Therefore, omega n is equal to square root of 12. So, what is the value of the square root of 12?
4 point something, sir. 3
Let
point something.
me check. 3.46.
Yes, sir.
Okay, 3.46. So it is 3.46. So this is the value of omega n. Now 8. That means 2 zeta omega n is equal to 8. So zeta, I don't know how to draw this using the mouse. Okay, 8 divided by 2 into 3.46. So we'll get the value of zeta, which is 8 by 2 by 3.46, 1.15. 1.15 value of zeta. So value of zeta is 1.15, which is zeta is greater than 1. So if it is greater than 1, then the output response would be overdamped, right? It is overdamped. Is it okay or not? Let me check.
Yes.
Yes, overdamped. Zeta is greater than 1. The response would be like this. Overdamped. This way you have to solve others. Okay. So what are the steps? First of all, you have to find out the value of omega n, then zeta, natural frequency and damping ratio. Find the natural frequency omega n, then the damping ratio zeta. Then based on the value of zeta, you have to identify what kind of output response the system will show. Okay, so you have to show this one. In this way, you have to solve all this. Okay. Similarly, another example is case message 4. They said that so see the zeta value 0.3. This is under damped. So zeta value 1.5. It is over damped. Zeta's value 1. This is critically damped. Zeta's value 0. The system is undamped. So you have to find the value of omega n and zeta, then you will decide what kind of response it would show. Okay. We are almost at the finishing zone. Okay. Now see the underdamped second order system. That means now that we have generalized the second order transfer function in terms of zeta and omega n, let us analyze the step response of the underdamped second order system. That means the value of zeta would be greater than 0 and less than 1. Not only will this response be found in terms of zeta and omega n, but more specifications and indigenous to the underdamped case will be defined. This is the common model for physical system. See, this display unique behavior that must be itemized. A detailed description of the underdamped system is necessary for both analysis and design. Okay. So, few things for underdamped system. So, let me see what. Let us see what is the underdamped system. This kind of system would be underdamped. The value of zeta would be higher than 0, lower than 1. So, this is the underdamped system. Okay. So, for the underdamped system, the rise time TR, the time required for the waveform to go from 0.1 to the final value up to 0.9 of the final value. This is the rise time. What is the peak time? Peak time is the time required to reach the first or maximum peak. See, peak time, the first peak, when it would go to the maximum point, that is called the peak time. Rise time 0.1 to 0.9 is called the rise time. And settling time, the time required for the transient damped oscillation to reach and stay within plus minus 2% of the steady state value. So plus minus 2% of the steady state value, that is called the settling time, TS. And percentage overshoot, that means the amount that the waveform overshoots the steady state or final value, the peak time, that means this percent, this is called the overshoot. Expressed as a percentage of the steady state value. How much? Excess. Okay. And another one, the evolution of TP. Oh, peak time. This is called a peak time. So this is the equation of peak time. Pi divided by omega n square root of 1 minus zeta square. And percentage of overshoot C max minus C final divided by C final into 100. This is the equation, or we can write the equation like this. We can use this equation also. In that case, zeta would be, if you have the percentage of overshoot, then you can easily calculate the zeta using this equation. Okay, you don't need other equations here. Now see, this is a chart. The changes, percentage of overshoot changes. Let's say 0.5. When the value would be 0.5, then what would be the percentage of overshoot? So 0.5 would be like this. Here is a value of 0.5. So value of percentage of overshoot here, maybe 18.5 for the 0.5 18. Or if you have the this 1.2, so maybe 55 or something like this. Now from the graph you can also find, from this curve which is known as the percentage overshoot versus damping ratio curve, you can also find out the values. And settling time formula 4 by zeta omega n. And rise time, what you have to find, let's say that this is the damping ratio, this is the rise time. So to find out the normalized rise time, you have to use this chart. See, this is the normalized rise time. So if you divide the normalized rise time by the natural frequency, that means the omega n, then you will find the actual rise time. You will find the actual rise time. Okay. So here is a problem. This is the last problem of this chapter. Given the transfer function, so peak time, percentage of overshoot, settling time, and rise time you have to calculate here. Peak time. So what is the peak time? So at first of all, you have to calculate the omega n, 10. Omega n should be 10, and zeta is 0.75. Equation 4.34. Now replace the equation 4.34. See, so peak time, you can find out the peak time. Okay, you can find out the peak time here. So peak time found at 0.475 seconds. Similarly, percentage of overshoot, 4.38 equation. 4.38 equation for the percentage of overshoot. Just put those value here, then you'll get the result. Then 4.42 and settling time again 4.42 equation for settling time 4 by zeta omega n. So you know the value of zeta and omega n, then you can find out the settling time. Now the thing is rise time, how to calculate it. Second, using the table in figure 4.16, in the normalized rise time 2.37 3 seconds. Okay, say the value of zeta is 0.75. Zeta is 0.75. So see, zeta is 0.75. That means it is in between 0.7 and 0.8. So what would be the value? 2.126 plus 2.426, 467 divided by 2. So they said that it is 2.3 seconds, roughly 2.3 seconds. So if you find the normalized value, then divided by omega n, then you will get the value. Okay. TR rise time to 0.23 seconds, dividing by this yields rise time 0.23 seconds. This problem demonstrates that we can find TP, percentage overshoot, TS and TR without the tedious task of taking inverse Laplace transform. Okay, so you do not need to take the inverse Laplace transform, rather you just find the values using the formulas given. Okay, so that was the final of this chapter. So we have completed this chapter, which is the chapter 4, time response. The name of the chapter is the time response. So we stick on the second order general system. Under damped second order system. Why we are considering this? Because it is mostly similar to the physical system. That's why we have chosen this one to know. Here the range of zeta is 0 to 1. Greater than 0, lower than 1. This is the value of zeta. So based on the value of zeta, we can find out the output response curve. We can find out the output response curve using the values of zeta. Okay. So this is our lesson from the chapter 4 of the Simon Nice. So guys, you have to check it on your free time. Okay, I'm uploading you today this video. Okay. So it was our